lecture 5, which is chapter 8 of your textbook. I'm going to look at air and our atmosphere and basically a little about air quality before we go into later on in the semester about how do we clean our environment. So in this chapter, what we're going to do is look at basically a little about what I'm going to call the anatomy of the atmosphere and where our biosphere fits into this. And also, what is weather? What's the difference between climate and weather? And why does this change? It's important for us in environmental science to understand the factors that create weather so we know better how to predict it, and even in some cases using a science called geoengineering to manipulate it to correct things that we've done in the past. So this will also include atmospheric circulation and explain why a lot of things like why hurricanes form and how global climate change could affect that. Then we're going to dig a little deeper into pollution. I'm going to see a supplemental video about air pollution too that looks at the major types of pollution, including a major one that's been around for many years called acid rain. So when we start thinking about the atmosphere and the breathable air, a lot of people just think that our atmosphere is composed of oxygen, and it's not really true. Actually, most of the air we breathe contains anywhere from about 75 to 80-something% nitrogen gas. Now, nitrogen gas is what we call inert. That means it doesn't have a chemical effect on us. It actually dilutes the oxygen. So it's not toxic to us, actually, because high levels of oxygen can actually be destructive to the body and almost act like bleach and would react with other molecules to basically tear our chemistry apart. So this is a very safe environment for us. And again, the nitrogen, mostly what it does is it gets into your body, into your blood, and you basically breathe it back out. The only time you run into issues with nitrogen, if you go up too fast in an airplane, I mean, you have to be faster in a commercial airplane, or when you're diving, you might end up with nitrogen bubbles in your blood if you were sent from diving too much. Now, the critical gas for us is oxygen gas, and that's about 20%, what we sometimes call 1 atmosphere, which is the perfect ratio for many creatures to stay alive. And then we find other things in the atmosphere, including certain types of gases, water vapor, methane, and particularly an important one is carbon dioxide, which is found in about very tiny amounts. And usually we pay attention to this carbon monoxide. It's usually found in about 0.0%, which is a fraction. But you need that percent to be a little high so that the Earth does have a blanket effect on it, that this low level of carbon dioxide does help to keep us warm. Too much warms us more. Too little could actually really create some problems as far as regulating temperature and also ultraviolet light that comes to the planet. But we really don't want the carbon dioxide too high too, because this can impede with our ability to remove carbon dioxide from the body and can cause our metabolism to shut down. So do be aware of the chemical composition of our atmosphere. And basically this concentration kind of spreads out as you get higher in altitude. And these ratios kind of stay the same, but the thing is, what we call their partial pressure or density does change with temperature too. So very cold air is much easier to breathe because the molecules are closer together and you have better access to them, versus warmer air. You still have the same ratio of these gases, but your relative pressure is less because you don't have as much access to these gases, particularly the oxygen. Another way to look at the atmosphere is to look at the pressure that the atmosphere puts on us. So when we look at this concept of atmosphere, the atmosphere is all the space above our head that goes up to, 50,000 kilometers, to the point where you're literally in outer space. And the way this atmosphere works, think of it like a liquid or even like a solid, and you're here on the bottom, and all these molecules, that's representing the molecules there, are sitting on your head, and what happens is these molecules press on those, press on those, press on those, to things that these are really dense and compact. So pressure of the atmospheric gases above us create this thing called partial pressure, which makes your atmosphere very dense in molecules, and that's what makes the air down here very breathable. When you start getting up here, to airplane depth, this gets enough to the point where there's not enough molecules in the air for you to capture enough oxygen to actually breathe. Now, removing CO2 is not a problem, but taking in oxygen, you can't take it in fast enough to keep your bodily processes going. Now, when I was flying at incredibly high altitudes, I encountered geese and insects and other things at atmospheres that were not livable to us. So just when we think about atmospheric pressure, just think about the livable environment for us. It exists as a shield called the biosphere, where creatures live in a thin skim of Earth, in which they get many of their atmospheric gases, but also other conditions such as temperature and radiation levels that makes the crust of our Earth very livable. And again, we measure this pressure in something sometimes called atmospheres, ATMs, or milligrams of mercury, or in barometric units of other types. Now, another important component of our atmosphere is the temperature of the atmosphere and the radiation levels. And we mean by radiation is that can be anything from X-rays to visible light, which is a form of what we call electromagnetic spectrum, ultraviolet light, which goes from near to far, and these lower numbers tend to be very destructive to our molecular chemistry. Some of these also tend to burn the skin and could alter our DNA. And X-rays is basically related to things called gamma rays, which can do harm to the body. So luckily, as we look at our atmosphere, part of the gases, the atmospheric gases, and also dust and other things in our lower levels of atmosphere, that means the mesosphere and stratosphere, which we'll look at in a little while, they absorb this radiation. So if our atmosphere becomes thinner, and that could mean even the air temperature overall gets warmer, these things can leak through. Cloud cover can block these things too, but cloud cover could also trap heat, which is trying to get out, and that could warm the Earth. So, but when we look at also temperature of the environment in itself, we can see that the lower atmospheres tend to be very cold and then to get extremely hot till we get to a certain points when you're in outer space, and then you're almost at what's called absolute zero, because there's almost no molecules up there to vibrate, because temperature is basically dependent on how many molecules are in an area and how dense they are and vibrating against each other. And you can also see the levels of gases in our atmosphere too. As you get up, they're very low, and then they get very high to the point where we find that they're applicable for our survival. So just understand this chart and understand that the atmosphere that we have, we really need to maintain. If we get rid of certain things like atmospheric ozone, it helps to block a lot of these destructive rays and protects us from some of the chemicals that do also rain down from our universe. So it is important to understand the height of our atmosphere and the different layers, because believe it or not, we produce pollution in all of these levels. So when we look at the bottommost level, which is about 5 to 10 miles thick, depending on where you're standing on the Earth, we have what's called the troposphere. And this is part of what we call the biosphere. That means the part of the Earth where humans live. And also a very important part of the hydrologic or water cycle. So just understand, this is the livable environment for us, the troposphere. The pressure is good, the gas ratios are good, and it has a moderating attempt on its temperature. We also find a lot of winds and most of our weather and climate occurring in the troposphere. Above the troposphere is the stratosphere. And I remember in the Air Force, we had planes that were called stratocruisers. And that just meant they went high up into the atmosphere, where you do find a lot of commercial jets in the lower part, and some small private jets and military jets can get much up higher than that. So this is an area that contains what's called ozone. This is what we call the good ozone. It's a very weird form of unstable oxygen called O3, where normal oxygen is O2. And sometimes it's called oxygen radical. It has a very strong electrical charge on it that basically makes it act like a degrading chemical. So it could be a very nasty chemical that's very unstable and could break down your chemistry. And it could also react with your molecules and cause what's called oxidation. Now that's not good to have ozone at the lower levels in the troposphere. This is where this does harm to us in the troposphere. But in the stratosphere, it protects you from a lot of deadly radiation. Then above the ozone layer or stratosphere is what we call a mesosphere or middle layer. And this is where first temperatures drop. When I was doing high altitude flights, and I mean, I wasn't flying, I was just, participating in the flight. I would watch the temperature gauge on the airplane go from down to minus 90, minus 80, even if we're over the equator, and then about minus 50, 150. I'm like, darn, it's cold up there. And you can actually hear the material, the plane creaking as the materials were getting tighter and basically putting pressure on the bolts and welds holding together the fuselage. So this is a very cold layer. But then when you get above that layer, we enter what's called the thermosphere above that. And this is a warm layer where a lot of chemical reactions are going on, and also a lot of radiation, dangerous radiation, is being absorbed. This is a very dangerous area for humans. Besides the lack of atmospheric gases, it's just a very hot, destructive part of the atmosphere. And this is where you hear about things like asteroids and spaceship parts and space dust that gets in there and burns up. So now to look at the layers of the atmosphere a little closer. There's your troposphere, and this is our livable universe. And you can see typically aircraft fly about this level, sometimes up there, because jets tend to run efficiently. You won't see prop planes there. And there's a little spy plane at one time when I was in the Air Force. That was confidential for how high they could fly. It was funny. Weather balloons come up into the stratosphere, but here's where your basically ozone layer is. This is called the upper atmosphere, and if you ever eventually get to fly in a spaceship, commercial spaceship for space tourism, this is the layer you usually go into right about here, usually not too much higher, okay, because this is what we sometimes call suborbital tourism flight. There's your mesosphere, which, look at the temperature, it drops off very dramatically, and then the temperature elevates as we go to the thermosphere. The thermosphere now we're looking at, you're getting close to outer space, which is a little legally higher than that. But we do find satellites up here in what are called sometimes suborbital or orbital flights. So suborbital just means that they kind of, the ship eventually comes down from orbit. This means they continue in orbit based on how they were set up and maybe little adjustments to their movement. So, and this is why you can see the International Space Station almost from Earth, because it's very low. We do have high altitude satellites too. Now, guys, when we look at pollution, 90% of our pollution occurs in the troposphere. And that's a problem because you breathe in the troposphere, it becomes part of the winds that spread across the Earth and part of the hydrologic cycle. When you start getting into more stratospheric pollution, now we're looking at things that can destroy the ozone layer. That means certain chemicals like freons, refrigerants, certain types of propellants, and microscopic motor oil particles can get up here and destroy the ozone, which can be destructive to the Earth. And then we have mesosphere and thermosphere pollutants that literally come from space travel and also from natural meteorites when they start to burn up and the parts burn up. And those rain down sometimes as iron dust or other materials. And some of the stuff that comes from the satellites are radioactive and contain toxic metals that rain down on us and settle eventually and then get into the tropospheric winds and into the hydrologic cycle. So in current history, since the advent of spaceflight, we have sent up tens of thousands of objects into this area of space, and is creating quite a lot of pollution that we don't know the full implications of yet. So a little earlier in the semester, we discussed this whole idea of abiotic factors. So what do we rely on the troposphere for, and basically the rest of our atmosphere, is it helps with the oceans. We've learned to determine weather, and weather means, like when we look at a forecast, it's a daily routine of precipitation or amount of sunshine or amount of solar radiation hitting the Earth, or sometimes even conditions like the amount of ozone in our troposphere from pollution. Climate, again, are long-term averages for weather conditions that are based on past models that we use to predict current patterns. And the and usually it's a 30-year average, which we're finding out now with global climate change. We're going to have to look at this at 10-year cycles now, and maybe even smaller, because our climate is changing so significantly. So don't look at a couple of abnormal weather events, like let's say it snows, in March in Houston, that is not climate change. That is a weird weather effect. Now, if it starts snowing regularly every year, that's now getting into something we better pay attention to as climate. So what else determines the temperature and has actually a major effect on the temperature of our atmosphere? And of course, this is the sun. So the sun provides us with heat, and the sun provides us also with types of radiation that don't normally produce heat, but when it bounces off the surface of the earth, it comes back off the earth as heat, which gets trapped by clouds. So temperature varies from one part of the earth to the other, and it has nothing to do with the closeness of the earth to the sun. So for example, our sun would be way, way out there, far away from us, at a point where we're not really feeling the full heat of the sun, the 40 to 80,000 degree temperature, whatever. The closest you come to feeling that temperature if you're ever struck directly by a lightning bolt and actually felt the heat of it. So what we're really feeling is the light coming from the sun and then penetrating our atmosphere. So when we look at the earth and the angle of the earth to the sun, the equator spends a lot of time with sunlight directly hitting it at a straight line. Now look, it does look closer to the earth, to the sun, but guys, it is not significantly closer than here. So it's not going to make a difference in the temperature as far as closeness to the sun, but it's that angle that's important. And you can even try this at home. You can put a warm light directly on your face, straight on, and then take the same light and put it at an angle away from you, same distance, and you will feel that light is actually cooler. So when light hits the earth at an angle, and that's like a 45-degree angle, believe it or not, the heat given off, or the heat that comes into the earth, actually acts cooler. So the more you get away from the equator, as long as the earth is at a perfect axis to the sun, the cooler you get. Now the earth does change in its angle from season to season, and this is why sometimes these hotter areas move up or move down, depending on where this angle is sitting compared to where the equator is. And usually the equator rocks within its own area where most of the sunlight is straight on. So think about this. When you're on the equator, the light is like this. You get a full intensity of light. It's all concentrated here, like concentrating light in a little area makes more warmth in a small area than here, where the warmth is spread out over a large area like here. So if you did not understand it, don't fret, but just know that the angle of the light that hits you from the sun determines the temperatures of a region to be cooler towards the poles, and the more that angle gets, like here, you get almost no heat coming from the sun, very little, enough just to, keep it from being very, very cold in those areas, colder than they are now. So another thing we have to pay attention to in the atmosphere is water vapor. Water vapor is, of course, part of the hydrologic cycle, so we need it for the production of precipitation and also for water to collect as it evaporates or transpires from the earth into the atmosphere. Water vapor has a shielding effect on the earth. It acts almost like a blanket. So water or water vapor and carbon dioxide, and you can also learn later methane. Some people call it methane, and both pronunciations are correct. Okay, so all of these act like blankets, that when sunlight comes down to the earth, that sunlight bounces off as heat from the earth, and this traps it. So water vapor provides us with precipitation, provides us with humidity that we need to help regulate our bodies and to make our atmosphere more breathable, and it also regulates the concentration of oxygen and other gases in our atmosphere. So humidity is measured in several terms, which are very confusing. But what's important to you is the humidity that you need to have adequate ability for your body to sweat, and also to have adequate humidity in the air for your lungs not to dry up. So air can be too dry and it can dehydrate you, or it could be too humid and it could prevent your body from cooling. And I've seen situations where the air temperature was 80 degrees and the humidity was so high that people literally died because their sweat could not evaporate from their body. And this happens a lot in industry, particularly where people have large tanks and containers that are going into, like the petrol industry, or sometimes someone's cleaning a water tank or another type of industrial tank, and it's so temperature is not always the killer. A lot of it is the relative humidity compared to that temperature that can do that. So do read up about this in your book about these terms. We're not going to go too much detail into them, but know that each creature has its own range of tolerance of the humidity it needs, as well as the atmospheric gases it needs to survive. So how do we put all this atmosphere stuff together? And probably what's most important for you to understand when we look at environmental science is how we use this in weather prediction, so we can look at, this whole idea is, how do we know climate is changing? How do we know when weather patterns are not what they're supposed to be, and things like that? So when we look at weather forecasts, usually you'll hear them talking in terms of highs and low pressure, which is also called, again, barometric pressure. This is a way of looking at temperature of air in these pockets that travel through various atmospheric winds, and even in just little cyclones of themselves. So this is looking at a typical weather map, and there's a low front, which means the pressure is low and usually associated with warmer temperature, where the pressure is real high, and usually associated with colder temperatures. High because the air is dense, low because the air is not dense, because as air warms up, the molecules spread out and give it less density, or in effect less weight. So we pay close attention to these, and these things, particularly these can menace us in the form of circular lows that can turn into typhoons or hurricanes. And you can also see the little symbols here that are used to also represent high and low, and the colors, usually we use a scheme of blue for high and red for low. So this is how we tend to read weather maps, and sometimes we'll even put the pressure here in whatever barometric units. So in summary, as I mentioned a little early, read about high pressure systems. These are systems, again, that are cooler air, okay, and you can see what are called like little isobars, which determine pressure differences within this unit itself. So I'm going to see different types of barometric pressures within here as we go along, and we use color coding to do that. So what else helps to determine our weather and conditions in our atmosphere? And we discussed this a little earlier with oceans, but lakes and land effects also have big effects, because wherever you find a body of water, particularly a large body of water, when solar radiation comes down to the earth, bodies of water tend to absorb that and actually store that heat. They don't give it off. When we have something like land, so let's say this is a piece of cement or a top of a building, as radiation comes in, that radiation slightly absorbs into that hard surface or the land, but much of it is given off in the form of heat. So when we look at sunlight, so if you're near an area with a lot of water, you tend to have a cooling effect from the sunlight coming down versus an area of a lot of land. And the color of the land makes a big difference too on how the light is reflected or absorbed. So darker surfaces tend to absorb more heat and then release it quickly when it's cooler, and lighter surfaces tend to not absorb heat, so they stay cooler to the touch, but the air above it is much warmer. And this is a great physics thing you can look up, but don't worry about it. So just know that water and land make big differences. And when the land is dark, it tends to hold that heat into the soil, into the material, and release very little during the sunny part of the day, but a lot at night. So a city, the streets feel very warm, and at night the streets give off a lot of heat, versus an area that's like colored white or very reflective. It gives off the heat as the sunlight is hitting it, but at night it tends to be cooler. So oceans work together with land and other bodies of water, and also work with the sunlight that's coming to the Earth. That means whatever angle it's coming at. Is it straight? Is it at an angle where this is cooler, that is warmer? So what we see, guys, is that as oceans and land heat, okay, and as the Earth rotates, and as different parts of the Earth heat differently, this creates all these different types of global air patterns that tend to circulate on the surface of the Earth, but also rise above the Earth and settle down. So you can see these things. They have different types of names called easterlies, types of winds that are produced at the pole. And then we have what are called these Hadley cells, which cycle around depending on where you are. So when we're subtropical, we see that the patterns are different than the tropics and different than the polar areas. So this is all so complex. And then the spinning of the Earth itself produces, you know, friction on the atmosphere that makes it flow too at winds up to 500 miles an hour sometimes in the upper atmosphere. Of course, closer to the Earth, friction of the air on the Earth slows it down a little. So this is amazing. So all these things, these cells, these flow patterns are all majorly affected by ocean temperature, by basically angle of the Earth. It's affected by the overall temperature of the Earth, and this is significant. And this makes it very, and all these factors contribute to the climate of an area. The climate of an area is dependent on latitude. That means where you are on the height of the Earth. Okay, it's dependent on whether you're near a body of water or not. It depends on your altitude, because that affects the density of the Earth and the heat holding capacity of air, and then the incident sunlight at a particular time of the year where the Earth is at a different angle. So you also hear these terms on the Weather Channel called prevailing winds. And again, these are just all phenomenons of the movement of the Earth and of these cells that produce continuous predictable winds. So just know some terms. You'll hear about these every now and then, called Hadley cells, which tend to be around the equator, and Ferrel cells, these are actually named after people, which tend to be cooler weather formations near the poles. And towards the center of the Earth, towards the poles, I should say. So, you know, understand, this is what determines your climate. And anything that causes a fluctuation of these is a problem. And it also means if we affect even the ozone layer of our Earth, is that certain areas like here can be overheated compared to what they're supposed to be, where here it might be safe. So depending on localized ozone thickness could make for a change in these Hadley or Ferrel cells. Humidity can have impacts too on how temperature is transferred through these cycles. One feature I've discussed before, called coriolis effect, is due to the spinning of the Earth and how this sets up winds that affect weather patterns, and also could also have an effect on large bodies of water, not small bodies of water. So we tend to see that particularly you see this most in hurricanes and in wind patterns in general, that when we're near the Tropic of Cancer, Tropic of Capricorn, these two areas about here, these mid-level regions, which to us is pretty warm for the United States, we find wind patterns like this that tend to cause oceans to swirl in that direction, and also hurricanes or typhoons to spin in that direction. And it's the opposite for the southern hemisphere, which we don't always pay attention to. The equator always has a straight line effect. Okay, but guys, this has nothing to do with small bodies. That means if you're walking, this doesn't affect your walking in a straight line, and it doesn't affect how toilets flush. It doesn't even affect ponds and whirlwinds and other things like that. So please understand that Coriolis effect is a major, major, big effect on how this affects our atmosphere and affects things in what's called the jet stream. That means this wind that is above the Earth that is due to tropospheric swirling due to the rotation of the Earth. So why don't we cover all these wind pattern things? Well, it's important for climate. It's important to understand how humidity is transported around the Earth and how CO2 is transported. But really what's very important for us is the whole idea that these atmospheric features, including even the gas content of our atmosphere, affects how atmospheric dust and pollution is transported. And guys, and we know atmospheric dust is a natural thing, but also humans can do things that create too much dust, particularly when we farm, we disrupt soils, we deforest areas. This dust can travel. And we do know that in the United States, we tend to get dust storms that sometimes come from California to us, and sometimes even come across from Africa to us. And some of this dust is natural. A lot of it is made by human activity, but this dust can sometimes have a major effect on weather patterns, and can also either suppress, sometimes tropical storms or storms in themselves, but it could also transport pollution and could also affect our health. Because if dust gets in your lungs, that could be a problem. So accompanying this video, you're going to have a video that just discusses the different types of pollutants, which we classify into primary and secondary. And I'm not going to go into too much detail here because the other video does a good job on it, and that's all it discusses. And that will be on the tests. So when we look at pollutants, we have these features called primary pollutants. And guys, pollutants can be natural or anthropogenic. That means made by people. And both of them are bad. Natural pollutants don't mean they're good for you, but this can include things like gases that come off from volcanoes, compounds produced by plants, I hate to say this, cow farts, which contain methane and other stuff, and as a matter of fact, termite gas is also a bad one. And so there are a lot of natural, what we call toxins out there, and also unnatural compounds called toxicants out there. So one of the big primary pollutants that we find, and this is also determined by governments too, is something called carbon monoxide. It's somewhat related to carbon dioxide, but not the same thing. Like what we talked about ozone, this is a very unstable molecule that tends to break down other materials. And also carbon monoxide can actually bind to the red pigment in your blood called hemoglobin that carries oxygen, and it can actually block your body from using oxygen, as stated here. And people that die from carbon monoxide toxicity or poisoning are actually dying from lack of oxygen. So this is a big primary one. Another category of primary ones are called particulate matter, and you're going to do a lab on collecting this. It's really going to be kind of fun. These are particles of dust, exhaust, compounds from burning stuff like coal and wood. So these are all different types of particles, including small soil particles that are about less than what we call 10 microns in size. And the problem with these is they tend to accumulate in your lungs. Now, the larger particles are sometimes blocked from your lungs by mucus and by, I hate to say, the hair in your nose. Okay, and some of them actually do settle out before getting to you. And some of them are easily removed by the lungs. But tiny particles can actually get through all your protective barriers of your lungs and sometimes even enter your bloodstream. And that can cause respiratory problems and eventually cardiovascular problems, and even sometimes affect your liver and all of your blood vessels. So this is a nice close-up of the different types of particulate matters. And guys, on a test, I would like you to know the size classifications. You're going to have this covered in a short video. So we have what are called a 2.5 micron size, which are the tiniest. Okay, the 10 micron size. Okay, which are the biggest, and they're actually in between. We sometimes measure the 5 micron size. So the bigger ones, and you can see examples of them, and the smaller ones, which are a lot of times the products of exhaust and industrial output, and even tiny slivers of metals, which you might collect in your air sampler that you make. Now, when you think of beach sand, which is very tiny in a way, and we're going to talk about this when we look at soils, it's jumbo compared to these molecules. Now, there's things called clay, which can also clay's about that big. It can sometimes get into your lungs too and act like a primary pollutant. So other types of primary air pollutants include anything that can be transported in the atmosphere as dust or attached to water or other fine particles, including clay dust. So it could be lead, mercury, all different types of what we call heavy metals or hazardous metals. It could be the breakdown products of fuels and breakdown products of coal and gases that come off from industry. Okay, so and then there's a big group of, like, called volatile organic compounds, or VOCs, and these are very big when we start looking at the manufacturing and the burning of plastics, the burning of fuels, and other, and even the burning of trash, which occurs. VOCs are very dangerous because they're associated with DNA damage, asthma, all sorts of types of diseases, including liver disease and premature death. Now, secondary pollutants are kind of weird because they're formed by other compounds we don't consider pollutants, but also they're produced by other pollutants that mix together. So secondary pollutants are manufactured in the atmosphere, and it's due to the fact that the atmosphere does have the presence of water and oxygen and ozone and other compounds like carbon monoxide that can react with these things. So we have chemicals called VOCs that we discussed, and something called nitrogen oxides, which are a primary pollutant, and they can interact to form something called smog, which you sometimes see it in Houston. It's like an orange haze, but it's really bad in other parts of the countries, and still it's bad in places where air sits stagnant, like on the California coast. Okay, so and then we also have ozone can interact with other compounds too to make complex smogs. And you'll hear about this in the video that talks about the secondary pollutants. So another area of atmosphere that's very subject to pollution is the stratosphere, which contains our ozone layer. Now, the thing is that this is what we call the good ozone, not tropospheric ozone, but stratospheric ozone. And this ozone is needed to basically, its main job is to block all the ultraviolet light that's coming from the sun, because if we didn't have an ozone, we'd basically be bleached to death with all the environmental, literally every aspect of the environment will be destroyed by this ultraviolet light. And our history of the Earth has gone through phases of ultraviolet light where it was much more destructive in the past. And today, luckily, it's at a level that we can survive. So just understand that some complex interactions go on that is a result of the oxygen in our atmosphere. And if our oxygen even lowers too much, which is possible if we reduce photosynthesis too much, is that this ozone layer will also decrease and cause some significant effects on the body. And in the past, there were many types of chemicals that we used to call fluorochlorocarbons, which are still used today in old air conditioning units, which can get up into the upper atmosphere and destroy this ozone. So just briefly, you can see here that we have developed ozone holes in our atmosphere, particularly over the Antarctic regions, and it affected Australia and New Zealand and Tasmania and even parts of southern Argentina. So, this was, you do go through ozone fluctuations, but never to the point that we did in the 70s with all the pollution that was entering the atmosphere. And once we got rid of this pollutant and banned it globally with something called the Montreal Pact, ozone layer in the stratosphere started replenishing itself. But this hole was fluctuating, but mostly hovering over this area and affecting the ice caps and the animals, and even affecting farming in areas around the southern hemisphere. So another big pollutant that our atmosphere produces, well, thanks to us, is this concept of acid, and actually it's called acid precipitation, because it's not just rain. It can be snow, it can be acid fog, it can be acid, hail. So this is comprised of the primary pollutants of sulfur dioxide and nitrogen dioxide mixing with water vapor in the atmosphere. And this can produce something called sulfuric acid and nitric acid, which, these are deadly acids when they come in contact with your body. And if they're concentrated enough, it could destroy things. And the problem is that there's been enough acid precipitation in our world now that it's acidified streams and lakes and ponds and even soil to the point where it's harmed plants and killed wildlife. Certain fish, amphibians, and insects and plants are very sensitive to pH, particularly acid pHs. And a lot of our statues and structures are too. And I know particularly in Italy and Greece, we've seen destruction of statues due to the acidity of the fog and the rain dissolving the statues. Florida has seen their soils literally limestone caves below the soils being eaten away by this acid precipitation, and this forms holes, sinkholes in the ground that could actually submerge houses and even a whole neighborhood. So later on in the semester, we're going to look at technologies that deal with pollution of different types, including air pollution. And the 1970s, when the EPA was being regulated, a lot of the push for the EPA was primarily air quality. Water quality was also very important, but air quality was a bigger one because we saw people dying immediately from air quality. We had many deaths throughout history due to bad air quality that killed up to sometimes 17,000 people in 3 days. So we started the Clean Air Act, just like very much we have a Clean Water Act, because again, air and water are primary things that we wanted to study. And with the advent of this act, we have seen reductions in pollution levels throughout times. And it doesn't mean that we've gotten the pollution down to a safe level. We've gotten it down to a barely acceptable level that we still could do a better job. As we come to an end, just listen to the other video that comes along with this lecture and look at your book as far as the different types of pollution, what their levels are supposed to be, and actually we measure it in amounts plus how much time you're supposed to be exposed to them. This is very typical in environmental toxicology. So it's not just how much, but it's how long you're exposed to it. And this is how we determine risk and benefit in health. And we'll get into this a little later. So, just go through this list and just get an idea of, basically the severity of some of these toxins that surround us all the time. So the list of toxins you've seen in the previous slide, we try to keep them to an acceptable level and even below that, because we know being at the threshold just means that a certain amount of people are going to get sick, and usually a large amount if we don't go below that level. If we want nobody sick, we'd have to have darn pure clean air, and it's almost impossible to do. So we have the Clean Air Act, the Energy Policy and Conservation Act is branched off from that because we know that most of our pollutants come from energy usage, which we'll see a little later in the semester. And our book takes us also into 1990s, where we've had various amendments that unfortunately right now are being rolled back. And this is going to happen from president to president, administration to administration. Sometimes they tighten the laws, sometimes they loosen the laws, sometimes we change the thresholds and the acceptable limits, and that's all part of how our government operates, because a lot of this is when we start looking at pollution control, it costs a lot of money to clean up pollution and prevent pollution. And sometimes with the prevention of pollutants, it does affect the economy, and it can make certain things expensive, like petrol and plastics and other stuff. So we got to think about this fine balance between having people dying in the street to have this wonderful economy, or have an economy that is a little less friendly, but having cleaner air that's affecting fewer people. And to close this lecture, I'm going to put you on a guilt trip, because all air pollution comes from us. It's a supply and demand market on how much energy you require to live and on the environmental footprint. So we have one of the highest environmental footprints per capita, per person. And that makes a big difference in the world, and we're big contributors to air pollution. So we got to think about the steps that we need, that we're really willing to do. So I am not ready to ride my bike to work, and I definitely can't walk to work. So I currently use a car that has pretty reasonable gas mileage. We can plant trees and restore forests, but there's costs and benefits to that. It's very expensive to live in an energy saving house, but the thing is that some people could afford it, some can't. And whenever we're trying to clean the environment, there's always a cost, and sometimes poor people can't be part of that because they can't afford the measures, and they're the ones that suffer from the pollution in their areas. So on that note, I'm done with this. Bye.